Welcome everybody, I am Giorgio Gobat, PhD student from Polytechnic Milano, Department of Civil and Environmental Engineering. Today I will present you an interpolation-based reduced order modeling for non-linearities in MEMS. Our goal is to model the gyroscope-like MEMS structure shown in this slide. The device was designed to study spring nonlinearities. The scanning electron microscope picture reports its dimension. The device is fabricated with surface micromachining and it is excited through combat rays placed on the four shuttle masses. The electrostatic force induces a beating heart motion named as drive mode and shown in the animation. The drive frequency is expected around 28 kHz. For the device modeling, one can consider full-order simulation technique, like finite element method. In these cases, the geometry and the physics of the device are modeled realistically. These approaches are powerful tools for both design and research, but they are computationally intensive. A finite element model may involve capital N degrees of freedom, with capital N ranging from few hundreds to millions of degrees of freedom. In the device considered, a structural mechanics finite element model referred to 1/4 of the whole structure has 664,000 degrees of freedom. In addition to this, multiphysics and nonlinear phenomena increase exponentially the computational effort. Because of that, we resort to reduced order modeling. With reduced order modeling, we intend the techniques that reduce the dimensionality of the full order problem. A reduced order model has only n degrees of freedom, with n far away lower than capital N. The reduction is done through simplifying assumptions. These assumptions may be given by projection in reduced spaces, or by the removal of degrees of freedom by application of special constraints. The technique here proposed is inspired by lumped parameter models. Lumped parameter models concentrate some physical properties of the system and assume that the masses are perfectly rigid, and the elastic elements have no mass. Let us consider the example in the box figure. Here, the full order system is given by a mass m suspended by flexible beams. The corresponding lumped parameter model apply a rigid body constraint to the mass and convert the beams into a spring of stiffness k. The system damping is lumped into a dashpot. The reduced order model here proposed use a similar approach and exploit interpolation-based nonlinearity mapping. The MEMS considered is designed to have stiff shuttle masses suspended by folded springs. The combat rays simply force the masses. Our reduced order model assumes that rigid bodies and compliant elements can be identified. In this way, the degrees of freedom are reduced to the one of the rigid elements only. Consequently, for each body, up to 6 degrees of freedom can be identified. The flexible elements can be lumped into nonlinear internal force functions, and the electrostatic components are lumped into external nonlinear force functions. The reduced order model construction can use the structure layout. The MEMS considered has two symmetry axes, and the combat rays are composed by fingers having the same dimension. This feature allows an efficient component lumping, since we can consider them as repeated modules, simply rotated and mirrored in the structure. The lumping procedure will give only 24 degrees of freedom, associated with 4 masses. As results, we obtain an electromechanical nonlinear reduced order model. A critical role is played by the nonlinear lumped functions that are described with interpolated maps or tables. To explain how the nonlinear force functions are modeled, we consider the example of a spring featuring geometrical nonlinearities. In the actual structure, this element is connected to the ground on one side and to the rigid mass on the other. Thus, the displacement it is constrained to the shuttle motion. To evaluate the effect of imposed displacement on these boundaries, one can perform static nonlinear simulation. In our case, we use finite element method. In this example, we consider an imposed motion along the x-axis, as shown in animation A. From this simulation, we can determine the reaction forces for each displacement considered. This gives the nonlinear internal force function consequent geometric nonlinearities. The results are shown in figure B, referring to the reaction force along the x direction. The same procedure can be applied considering a displacement in the z direction, displayed in figure C. In this way, we get the nonlinear force function in the x direction discretely, plotted in figure D. This process can be done also for combination of displacement on the two directions. This will give, in a discrete way, the surface of the internal force function. An example is shown in figure E. Between the sampled points, one can fill the gap with interpolations or fitting method and reconstruct a continuous internal force function. This concept can be extended considering 3 displacement and 3 rotation applied to the boundary of the spring element. This will produce a table that relates uniquely the element configuration to the reaction forces applied to the rigid mass, and thus the nonlinear internal force function. As mentioned, also with 6 configuration parameters, the gap between the sampled values can be filled with a fitting or interpolating procedure. The same concept can be extended to electrostatic components. Here, one will consider different electrode configuration, and for each one, the electrostatic force on the rigid mass is computed. In our case, we used boundary element method simulation for the mapping. The reduced order modeling procedure can be summarized as follows. We start from a trial configuration Q of the system. From it is possible to evaluate both mechanical and electrostatic forces through interpolation procedures. Once the nonlinear forces are known, the system equilibrium can be evaluated. In our case, we are interested in the dynamic problem, thus the Lagrangian equation of motion is solved. A new configuration Q at time 1 is defined. Because of nonlinearity, this configuration will not be the correct one. Consequently, a Newton-Raphson iterative process is applied. The nonlinear forces are updated until the residual is under a certain threshold. Once the convergence is reached, a new step can be evaluated. Applying this procedure to the structure considered, we first check the eigenmodes. Our results show an error lower than 0.5% respect the equivalent finite element model. The drive motion is properly reproduced. The full order model and the reduced order model results are shown in the animations. As well as the drive mode, also higher frequency mode can be simulated, but to higher frequency corresponds lower precision. This happens for 2 reasons. First, the rigid mass assumptions neglect the compliance contribution of the shuttle. This makes the reduced order model stiffer than the full one. Second, the interpolation procedure is an approximation of the full order force function. Therefore, this introduces a small error in the reduced order model. Then we compare the reduced order model results with the experimental data. The comparison is done considering the frequency response function of the device when excited through the combo rays. The device is excited with a VDC of 10 volt and a VAC of 2 and 1 volt respectively. The reduced order model results is obtained using a numeric time stepping algorithm. The electromechanical reduced order model simulation have an excellent agreement with the experiments. The maximum amplitude and the nonlinear behavior are comparable. In conclusion, the reduced order model proposed can model properly electrostatic and geometric nonlinearities and allow a strong dimensionality reduction compared to equivalent finite element model. Among its advantages, we have that it is physically based, thus simple interpretation and reconstruction are possible. The interpolated maps of the non-linearities are versatile because they are not constrained by strong assumptions. Also, a lot of eigenmodes are retained in the reduced order model, thus quite complex behavior and interaction can be simulated. There are also some drawbacks in the method that is not effective in structure where the compliant and stiff elements cannot be separated. Here, the reduction process will give worst approximation. Another limitation is given by the non-linearities mapping procedure that is crucial for the model quality. It must be carefully tailored, considering both the precision required and the range of motion expected. As future application, we aim to simulate all the possible nonlinear interaction in the device, such as internal resonances. Thank you for your kind attention.